Hi, in this video I show you how to analyze time efficiency for recursive algorithms, and the one that we use in our example is to calculate the power of base x to the power of exponential, right? So we have this algorithm. If the exponential is 0, then we just return 1. Otherwise, we get the base x multiplied by the power base to the exponential minus 1, right? So how we can analyze the time efficiency for this algorithm? There's a few steps. The first one, we trace how the algorithm works. The second one, we try to count the number of basic operations. Sometimes we try to come out with the formula as well, and from a solved formula we try to get the big O notation. So let's do it step by step. Okay, let's start. Right, so the first one is to trace how the algorithm works. Right, so let's start. So we give some input here and some input here. Let's say that I want to compute power of 3, 5. In order to compute power of 3, 5, so 5 in here, right, it's not equal, so it's come here. I need to compute the power of 3, 4. So now, in order to get 3, 4, I need to compute power of 3, 3. I need to compute power of 3, 2. 3, 1. And finally, power of 3, 0. When exponential becomes 0, so we get it here. And it's return 1, so it's complete already. Now we need to count, right? So number 2, count the number of basic operations. Okay, so let's ask yourself, how can we count the number of operations when, you know, for example, x equal to 3 and 5 here, so 3, 5 here. So this is important. From this line of code, we see that number of operation, basic operation for power of, for example, 3, 5, it will be equal to, so in order to get this, right, to count the number of operations for this, we need to know the number of operations for this first. And it's become number of operations for power 3, 4, right? This one minus 1, 5 minus 1, 4. Together with one more operation with a x multiplied by the result. So this is one more operation, x multiplied by result, plus one more operation, and this operation is x multiplied by this power of x and x exponential minus 1. So in here, actually, this one is 3, 2, and 3. So this is one more operation, right? So in order to get this 3, 5, we need to count the 3, 4 plus 1, right? And the same thing, in order to get 3, 4, we need to count for 3, 3 plus 1. And in order to get 3, 3, we need to count for 3, 2, which asks us to count for 3, 1, which asks us to count for 3, 0. And because of that, we have this here. So we ask ourselves, how many basic operations for 3, 0? Exponential 0, then return 1. One operation only. So this is one operation only. This is return 1. Now, this one equal to whatever 3, 0 plus 1, right? So it means that 1 from here together with 1. 1 is here. 1 is this one. X multiplied by power x exponential minus 1. So in here is what? 3 multiplied by power of 3. 1 minus 1, which is 0, right? So when this one 3, 2 is will equal to whatever number of operation of, so 3, 1 together with 1. So this one is equal to 2. This one is 2 from here plus one more operation. So it's 3. And now you have the filling, right? Again, 3, 3, we need to count the number of operation of 3, 2. What is 3? Together with one more operation, what is, again, x multiplied by power x exponential minus 1. So this one is 4. 4 plus 1, this one is 5. 5 plus 1, this one is 6. Okay, so we're done with 1 and 2. So we've done 1 and 2. Now we try to generalize to get a formula. So how to do that, right? So in here you say that is there this result, this number of basic operation, is it depend on something? You see that here it's actually, it does not depend on the x, does not depend on the base, but it just depend on the exponential. So if the exponential is 0, then we have 1. Exponential 1, the number of operation is 2, and etc. So actually we'll have the function t based on the exponential, and actually this one is become the exponential plus 1. You know why, right? Because 0, then I get 1. Exponential 1, then I get 2 number of operation. Exponential 2, then we have 3, and etc. So the time to run this algorithm depends on the exponential, and this is equal to the exponential itself together added 1. Right, and actually in the computing, right, we don't use exponential, right? We use n, right? So we say Tn equal to n plus 1. So this is the formula we have, with n is the exponential from the input. So we done 1 and 2. Now the last step is we try to obtain or get the big O notation. Right. So in here we look at the Tn and we look at which one will be significant when n's become very large, and we know that 1 is just doesn't matter, only n. So we say that big O of this algorithm is actually big O of n. So in this video I show you one way to analyze the time efficiencies of a recursive algorithm. So the first step, we will see how the algorithm works by giving some of the example input. So in here we'll have this how it's working here. In order to run the 3.5, we need to call 3.4 and etc. until 3.0. Our next step is to count the basic operations, and we see that from this formula we know that in order to compute the higher, we need to compute the lower until 0, and because of that we work from 0, and after that we work to 1, work to 3, and etc. So we can count the number of basic operation. After that, we try to get a formula from what we have based on the input, and we realize in this situation that the time to run only depends on the exponential, it's not depends on the base, and actually the total of number of operations is actually based on the exponential together with 1, right? Because here we have 1, 2, 3, etc. After that, we get the big O notation from the formula in here. Right? I hope you enjoyed the video, and thank you very much.